Hello, everyone. Welcome back. So today we want to learn about the first derivative test and how we use that to find local maximum minimum values. So our goals, understand the relationship of the derivative to increasing, decreasing functions. That's been kind of our first step in doing this. Understand that. And then we'll actually talk about what the first derivative test is and then how to use it to find local maximum and minimum values or maxima and minima. So first, let's talk about increasing and decreasing functions. This is something you've probably seen in algebra before. You might have also mentioned it in other calculus topics. But remember that a function is, if a function is increasing, we think of it as going upward from left to right. Okay. And it turns out a function is going up from left to right. The first derivative in that part of the graph is positive. So if a function is increasing in some place, the derivative of that place is positive. In the same way, if the function is decreasing, that place is going down from left to right, and then the derivative is negative. And basically, when we think about this, is remember that the derivative gives you the slope of a tangent line at a certain point, and this works just like slope. So if we remember from algebra that if a slope is positive, the function is increasing, and if the slope is negative, the function is decreasing. Let's come over here to the right, and let's just look at a basic example, one we're all familiar with. Well, try to do a better job of drawing it. Y equals x squared. So a parabola. Okay. Now, obviously here on this side, okay, this side of 0, it's obviously increasing. Okay, it's going up from left to right. Think about a tangent line right here. It's positive. So on this side, just say from 0 to infinity, okay, f prime of x is positive, it's greater than 0. Okay. And then on this side, it's obviously decreasing. Think about the slope of any tangent line on this side. And basically, it's going to be negative. So from negative infinity to 0, then your derivative is decreasing. Okay. And of course, we can see that because we think about, to be consistent, let's call this f prime of f of x. Okay. Because, of course, f prime of x is 2x. And obviously, you plug in a positive value, this is positive. You plug in a negative value, it's negative. Okay. So just remember that where a function is going up from left to right, upward from left to right, the derivative is positive, which is going downward from left to right, the derivative is negative, or it's just like the slope of a line, because a derivative is a slope of a tangent line. Okay. Now, more in general, let's think about an imaginary function here, a made-up function. And let's also think about what that implies. The more thing before we leave this one, if you notice right here, at 0, okay, basically, if this function is continuous and there are no corners, no gaps, no holes, so our derivative is defined everywhere. So right here at 0, then basically the derivative is equal to 0 because it changes from derivative changes from negative to positive. Okay, so we'll talk about that next. Let's imagine an imaginary function here with several features. So let's say we have a function that looks like this. Okay, this is our function f of x, and there's a lot going on. Let's talk about it. Okay, so let's kind of think of it the same way. Let's call this point A, B, C, D, and E. Okay, now we can think about what's happening here. Let's say this also kind of goes forever in both directions here and also at the end. Okay, now if you notice, let's take a look. So let's apply this general function here, right? So what we can say then is where this function is increasing, and that means that the derivative greater than 0, okay, where is that? Well, basically here, this first part, you see it's going up from left to right. You go from left to right. I always think it was going from left to right. You're going up here. The thing about a roller coaster, you're going uphill, okay, from negative infinity to A, okay? Also from B to C, and also with increasing, decreasing, we don't include endpoints, okay? And then where else is increasing? From D to E, and so forth, okay? That's where it's increasing, where it's going uphill. Now, where is it decreasing? And I think you get the idea, so it's decreasing. Where is it going downhill? And that's where the derivative is negative. And it's going downhill from A to B, essentially everywhere else, from C to D, and then from this case, the way it shows from E to infinity. Okay. Now, another thing, where is the derivative 0? Okay, so our derivative is 0. Well, basic here, this function is continuous. It's also we call smooth. Basically, the derivative exists anywhere, no corners, no holes. So basically, it's 0 right here at A. Okay, and also at B, 0 at both those places. And as we can see from the graph, we actually have a local maximum at A and local minimum at B. If we're going from increasing to decreasing, we have a local maximum. Going from decreasing to increasing, we have a local minimum. Now, a couple other places, right here, the derivative is not equal to 0, okay, over the corner. What that means, derivative changes instantly from positive to negative. So it's not equal to 0, but doesn't exist. So f prime of x does not exist at a couple places. X equals c, okay, right here. Actually, d also, here also doesn't exist because this function is discontinuous. And so at x equals d, and also, of course, here at e, you have vertical asymptote, so x equals e. All those are places where the derivative does not exist. Okay. Now, one more thing. Where do we have the local maximum and minimum values? And squeeze it in right here. So local maximum, you have one of those, you said x equals a, and also x equals c. Okay. Then a local minimum, actually only one of those we have is at x equals b. Now, if you remember, or if you've seen one of the other videos about this topic about derivatives, or also about local maximums or minimums, or other topics or other videos, basically here, since it's not continuous, although this is kind of a locally lower point than other points, it doesn't classify actually the local maximum, local minimum because the derivative is not defined there. Okay. So mainly today, we're going to focus on places where it's continuous, like from here, we're not going to focus on discontinuities or vertical asymptotes. Focus on situations like these. Our goal then is to be able to find local maximums or minimum values. And we can do that then using understanding of the first derivative. So if we have a continuous function, like this first part up to, let's say up to D, have a continuous function, and it changes, the derivative changes from positive to negative, or the other way around, from negative to positive. And those places are going to be where we have a local maximum or minimum. That's what we want to look for. So that's going to bring us to the first derivative test. Okay, so the first derivative test, it says, back to the left, says assume a function is continuous in some interval containing a critical point C. Remember, critical point is a place, like we saw here, A, B, C, D, and E, where the derivative is either 0 or doesn't exist. And here we're talking about continuous functions, so we're just going to focus on places where it's continuous. Then, what it says, if f changes sign from positive to negative, you have a local maximum. And that's what we saw at point A. Here, also point C, it changes from positive to negative. You have a local maximum there. It changes from negative to positive, you have a local minimum like we saw at D. If the sign does not change at C, then there's no local maximum at C. And that can happen as well. We'll mention one of those. That can also happen sometime. Okay, so let's look at our first example of using the first derivative test. Let's come back over here. All right, so let's start with a function, and we'll kind of see how this works and how we can actually find it. Now, I also admit that a lot of these things I'm about to show you are techniques that are really important before calculators and computers, when people couldn't easily graph functions, so they need other ways to be able to figure out what the graph is, especially to find local maximums and minimums. So they use these techniques, and these are still good for understanding, although they're not as important for visualizing a function anymore. They're still really useful for understanding what the derivative tells us and also about the function. So number one, so let's say we have this function, f of x, and we'll talk about how to do this. Negative x cubed over 3 plus x squared over 2 plus 2x. Okay. Now, so what we want to do then is we want to find basically local maximum and minimum values, and also find where it's increasing and decreasing. Okay. So the way to do that, first step, is take the derivative. Okay. Since all this depends on where the derivative, what the sign of the derivative is, then we need to do that first. So take the derivative. So f prime of x is going to be 1/3, that's the constant, times derivative of negative x cubed. Well, it's negative 1/3. The derivative of x cubed is 3x squared. Then plus 1/2 is the constant in front, and think of it that way. Derivative of x squared is 2x. And then finally, over here, the derivative of 2x is just 2. And then let's simplify this. So it's nice. The 3's cancel out here. The 2's cancel out here. What we're left with is negative x squared plus x plus 2. Okay. Now, that's our derivative. All right. Now, that's good, but then how do we figure out, first I need to find like where it's 0 and also where it's increasing and decreasing. And so just looking at it, we can't really tell that right away. Now, if you recognize this is a quadratic function, so the graph's a parabola, but it's not easy to tell just by looking at it where it's going to be positive or negative or 0. So first off, let's find where it's 0. Let's find the critical point or points. Remember, to do that, we basically set equal to 0 and solve. Okay, so negative x squared plus x plus 2 is 0. Now, this is one, it's a quadratic, so you could always use the quadratic formula, but actually I'm going to factor this. It's a little bit quicker. Now, also, one thing I'm going to do, this isn't necessary, but it's easier to factor if we don't have a negative right here. So what I'm going to do is I'm going to factor a negative out of this side. Take a negative out, so it's be x squared minus x minus 2 is 0. And then I can actually just divide everything by -1 and get rid of the negative altogether. Once you don't have to do that, but it does make it easier to factor. Okay, so now I have x squared minus x minus 2 is 0. And if you factor that, it's going to factor into x minus 2 and x plus 1. Okay, so remember here, to solve this, set each factor equal to 0 and solves. X minus 2 is 0, x plus 1 is 0. And so our factors, our critical points, are 2 and -1. So these are our critical points. Remember, these are where the derivative is equal to 0. All right, how we're going to do this then, how we're going to help us figure this out, is we're going to set up a something's called a sign chart. It's kind of one way to help us out with this, to kind of visualize this, to understand exactly where the derivative is positive and negative. Okay, remember, this is our derivative, so the sign of this is going to determine whether it's positive or negative. Okay, so what I want to do is we have two critical values. We're going to separate our real line into where our critical values are. All right, so we have one at -1 and 2. let's say this is 0 right here. This is -1, x equals -1. This is x equals 2. All right. Now, what I'm doing is I'm just going to call this something called a sign chart. It's kind of a way to do this by hand. And also, we'll look at this function here in a minute to make sure we'll graph it to make sure we got it right. But this is going to give us an idea of how this works. Okay. What I'm going to do is I'm going to put both my factors, x minus 2, actually, it's over here. Actually, I need one more separator here and put my factors over here. So this is going to be x minus 2. And then, in fact, you know what? Let me just make this a little better. Put my numbers up here. This is 0. This is -1. This is 2. Okay. X minus 2 and x plus 1. And then right here below, I'm going to write the sign. Okay. Now, what our critical values do, they divide basically, these are the places, critical values, where the derivative changes sign here. So I'm going to write that down. So the derivative changes sign at the critical values, at the critical points. Okay. So what that means is that's where they're going to the derivative is going to go from positive to negative. So a way to figure that out is look at the factors of our derivative. Okay. These two numbers multiply together. So just remember, so we have two factors. If you multiply two positives together, you get a positive. Both these are positive, the derivative is positive. If both these are negative, negative times negative is positive, it's also positive. And if they're opposite signs, and it's negative, so your derivative is negative there. What we're going to do then is for each one of our factors to make this up, we're going to find out its sign on each interval, okay? This number right here is based from -1 back to infinity. This is between -1 and 2. This one is between, it goes from 2 to infinity, okay? Now, let's think about, so imagine plugging in a value here, plug in something for -1 in here, okay? So maybe -2. Plug in -2 in here, -2 minus 2 is going to still be negative. We don't care about the value, we care about the sign. It's going to be negative. Okay. We plug in anything between, say that's -2, and maybe here it's just going to be 3. So these are test values. Okay. Now, what about here? We plug in 0. Any number between these two will work because we know that the derivative doesn't change, it stays the same sign between -1 and 2. Okay. So plug in 0 here. And then that's still going to be 0. 0 minus 2 is still negative. Okay. And then finally, if you plug in a 3 in this interval, it's going to say the same sign in this interval. This factor will. If you plug in a 3, 3 minus 2 is 1, that's positive. And also, if you notice, as you probably expect, it's going to change sign. This particular factor is going to change sign right here from negative to positive. Right? Same thing down here. I plug in a -2 in here. -2 plus 1 is a negative. And as you expect, these are going to be positive. They will be. We'll plug in a 0 here for x. 0 plus 1 is positive. And then whereas 3 plus 1 is also positive. Okay. So now, let's take a look. So this is the sign of f prime of x. Let's see what we have. Right here, both these factors here are negative on this side of -1. Negative times negative is a positive. Here, both of them have opposite signs. We know that's a negative. Okay. And here, they're both positive. That's definitely a positive. So what that tells us, okay, tells us that's the sign. So one more thing we know, the function is increasing here, where it's positive. It's decreasing in between -1 and 2, and then it's increasing here again, essentially from 2 to infinity. Also, what it tells us, go back to our first derivative test, it changes from increasing to decreasing at 1. So that means we have a local maximum value at x equals -1, since it goes from increasing to decreasing. Then here, 2 goes from decreasing to increasing, so we have a local minimum at x equals 2. Okay? And so if we graph that, do a really basic graph, once again, this is just a very, very basic graph. Okay, so here is -1. Here's 2. Okay, so remember that's where the function changes. So it's going to look something. We don't know. We didn't investigate so where it crosses where the function itself, um, crosses the x-axis. It looks something like this. So it's increasing here up to 1, then it's decreasing till we get to 2, and then somewhere it's decreasing and then it increases again. Okay. Now it's not going to look exactly like that. Let's graph it and see what we see what it is. But that's going to be essentially a basic shape. And if we did more work, we can also look at the function itself and find out where it crosses the x-axis and so forth. Okay. We can also find the value of the local maximum and minimum values if we want. Okay, so let's graph that. Let's go to Desmos. Let's just verify what we have. So negative x cubed divided by 3 plus x squared divided by 2 plus 2x. And yeah, as we saw. So the shape is a bit off, but right here at 1, once again, we said we have a local wait a minute. Okay, hang on. And I just realized I did something, so hopefully you see what I did wrong. That's bad. All right. Well, what I did here to find my critical values is perfectly legitimate. I just forgot about this, but still, this was a negative right here. Okay, this is important. We just found out that we made a mistake. So what I need to have remembered is actually still have a negative in front. So we had a negative sign. Let me see how to fix this. I apologize for that. I wasn't more attention. Remember, we also had a negative right here. So I put that negative right here as -1. That's one of our factors, essentially. Okay. And this is for f. Let me write this again. F prime of x equals negative out front x plus 2, x minus 2. X plus 1. So I forgot the negatives. Okay. So it's negative everywhere. Is what that's going to do. That's going to change all our signs. So I was going to apologize for that. I just wasn't paying attention. But this is something good to see because this can easily happen. So once again, I didn't do anything wrong and find my critical values, but at the same time, by dividing this negative out, I actually changed my signs. Okay. So that's a good reason why it's helpful to graph these things. So we do that. Actually, this just changes all our signs. Okay. So 3 negatives make a negative. Okay. A negative, 2 negatives, and a positive make a positive. And then a negative and 2 positives make a negative. All right, so we just have to change these labels here and change those, and also just go ahead and erase this. We'll fix that. Okay. All right, so if my sign is negative, that means it's decreasing here. If the sign of the derivative is positive, it's increasing in this interval, and then it's decreasing again over here. Okay, so at -1, we go from decreasing to increasing, so that's a local minimum at x equals -1. Go from increasing decreasing at 2, that's a local maximum. All right, so just got those backwards. So local minimum at 1, -1, local maximum at 2, so it looks something, once again, like this, and exactly where it crosses the x-axis and all that, you can also find that out from the function itself. Okay, that's the basic shape of it. It looks something like that. So now if we go back to the picture, but yes, be careful. So make sure if you do that, make sure you include the negative. Even if you get rid of the negative like we did to find your critical values, make sure you include that negative in the sign chart. Okay, right. So it looks basically like that. So once again, here at -1, we have a local minimum, and 2 have a local maximum. Right. So that makes sense. Okay, so that's the idea. We can find out where it's increasing, decreasing. And then also we can say a few more things. So the function is, where's the function increasing? Okay, so it's increasing between -1 and 2. All right. And where is it decreasing? The intervals where it's decreasing. Remember, increase and decreasing intervals, you don't include the endpoints. So it's decreasing from -infinity to -1. Okay. Then also is decreasing from 2 to infinity. And we're going to write the union symbol in between. Okay, that's right. It's increasing, decreasing, and constant. Okay, let's do a couple more of those. So, that was number one. Number two, let's do a trig functions. This time our f prime, sorry, f of x is equal to -2 cosine of x minus x. And here we're looking at a specific interval from 0 to 2 pi. Okay. Now, so here we want to do the same thing, but just on this particular interval. Now, first thing, let's actually graph this one first. Okay. So that way we can kind of match up. That's always a good thing to do since you have graphing tools available to graph it first. So let me actually turn this one off. And so let's graph this. And you don't have to put it y, put it as y equals this. Y equals -2 times the cosine of x minus x. Okay. Remember also this Desmos, the default setting is in radians. So I'm keep it in radians. Okay. Now, it goes from 0 to 2 pi. So also a useful thing you can do is you can also graph vertical lines on Desmos. So something useful to do here is just type in x equals 0. A vertical line, of course, that's the same as a y-axis. And also let's do x equals 2 pi. To do pi, you just have to type in pi, okay? What that does, this kind of shows you exactly where the limits of what we're interested in right here. So this part right here, okay? So as we can see, we should have a local minimum right here and also a local maximum right there. So we'll make sure, I'm going to tell where they are, make sure that's what we get when we finish this. But let's go through basically the same process. Okay, so once again, I want to find the derivative. That's where I have to start. Tells us where it is increasing, decreasing, and 0. And so that's f prime of x is equal to -2, and the derivative of cosine x is negative sine of x. And then derivative of x is 1. And so this is just going to be +2 times the sine of x minus 1. Okay, and that's our derivative. All right. Then, once again, like we did last time, find your critical values. And so I'm going to solve 2 times the sine of x minus 1 is equal to 0. Okay. Now, of course, get the sine of x by itself. Let's add 1 to both sides. We have 2 times the sine of x is equal to 0, or equal to 1. And then divide both sides by 2. So the sine of x is equal to 1/2. Okay. This goes back to solving trig equations. So this is something we're bringing like the unit circle, for example. But basically, this has solutions. So x is equal to, so what makes the sine of x equal to 1/2, whereas sine of x equal to 1/2. And basically, once again, we're just interested, of course, if you think about the full sine of x graph from negative infinity to infinity are all real numbers. You have an infinite number of these places, but in the interval from 0 to 2 pi, you just have two values, pi of x, or pi is over 6, and 5 pi over 6. Okay, where the sine of x is equal to +1/2. Okay, so these are our critical values. Once again, these are the places where the derivative is equal to 0. All right, so much like we did the last example, what we're going to do then is actually let's take a look at our derivative, and basically we want to find out what the function does on either side of these values. Okay, and also let's approximate those. So that's something we can also do on Desmos. So pi over 6, go back to Desmos. All right, once again, do a pi, just type in pi divided by 6, and it's about point, and here we just wanted an idea of the approximate value, it's about 0.52. Okay, then 5 pi over 6. And you already see those values right here, kind of give it away, but make sure we get the same thing, about 2.61, 0.52 and 2.61. So It's approximately 0.52 and about 2.61. Okay. Now, let's do our sine chart. Okay. So these values separate everything. All right. So this is pi over 6, which is approximately 0.52. And this is 5 pi over 6, which is approximately 2.61. Okay. Now, remember, it's going from 0 to 2 pi. So maybe a good idea to make another division right here. Here's 0, and here is 2 pi. Okay. All right. Now here, this one is, let's take a look at our derivative. Okay. Now, one thing about this derivative is we still think this is a sine chart, but here we don't really have a really nice, there's no really way to factor this the way we did the polynomial. Okay. What we have to do here is just basically plug in values. Okay. Pick values. That's why I gave you this number right here. Use the decimal. Okay. So let's pick a couple test values in between. Here we just use decimals. We can actually use decimals or your calculator to figure this out. Just make sure your own calculator, make sure you're in radian mode. Okay. This is 0.5. Let's go to say 0.25 is our test value. Here in the middle between these two, let's just do 1. Okay. 1 is a good one between 0.52 and 0.21. And then here, 2.61, where it's 2 pi is about 6 point something. So how about 4? That's good enough. Okay. So we're going to do here, of course, this is our derivative, 2 sine of x minus 1. What we do is just plug those values in and see what we get. So we have multiple factors. So let's go back to Desmos. And we'll double check, make sure you have 2 times the sine of x minus 1. 0.25, 1, and 4. So what we can do then is write 2 times the sine 0.25 minus 1. And that's about negative 0.51. That won't really care about, we don't really care about the value, we just care that it's negative. So it's negative there. Let's go back and put that in. So here is the sine of f prime of x. It's negative. Okay. Now, it's probably going to be positive here, but we need to verify that. So let's plug that in. So plug in 0.52. Okay, and I'm actually just going to use it of typing again. I'm going to use the same thing. So 0.52, we did it 1. Okay, so at 1, yeah, it is positive, 0.68. And then again, our test value here is 4. Let's plug that in. All right, and once again, as expected, it's negative there. Okay, so it's negative on that side. Okay, so as we can see, where it changes, so what we can see then, that's the sine of x. So basically, let's kind of continue this table on down. So here it's obviously decreasing, increasing in the middle, and decreasing on this side. So we can say then is where the function is increasing. Let's go just from the range from 0 to 2 pi. It's increasing from pi over 6 to 5 pi over 6. Endpoints not included. It's decreasing the other two places. So that's from 0. In this case, well, so 0, although we don't include the endpoints. Although in our original interval, 0 is included, we don't include the endpoints for increasing, decreasing. It's decreasing from 0 to pi over 6. And then use the union sign. Then again, from 5 pi over 6 and to 2 pi. And once again, although 2 pi is included in the original interval, we don't include it increasing and decreasing. Then the last thing, at pi over 6, it goes from decreasing to increasing. So that's a local minimum. And then it goes from increasing, decreasing at 5 pi over 6. That's a local maximum. So we identified the areas where it's increasing, decreasing, also identified where it's the local maximum, local minimum values are. Okay. Yeah, and once again, if we look at the graph again, we can verify that. All right, let's zoom in a bit. All right, so as we saw, you can see this from Desmos right here. Yeah, so at pi over 6, we have a local minimum, as we said. It's decreasing from 0 to there, and then increasing here, then here at 5 pi over 6, local maximum. Then it decreases all the way to pi over 2. All right, good. Okay, let's take a look at one more of those. Number 3. All right, let's look at one, maybe a little more function, a little more going on as well. So x times e to the negative x squared over 2. Okay, so once again, we'll graph this first. And it's always good to graph it first. So y equals x times e raised to the, here, I'll do negative, I'll just use parentheses. So x squared divided by 2. Oops, I'll also be careful. So x squared. Then make sure Desmos, if you saw what happened right there, if I don't do a little arrow and get out of the exponent, it would read that as exponent of 2 over 2. That's not what I want. This is what I want. Okay. Oops, also let me turn this other graph off. And turn those horizontal lines off. Yeah, there we go. Okay, so you see what this graph looks like. Okay, it looks like we should have a minimum at -1, a maximum at +1. So let's double check, make sure that's the case. You realize we didn't draw the last graph, but that's okay. You saw the graph on Desmos, you can graph on our graphing calculator. All right, so once again, like usual, let's find our derivative. Okay, so f prime of x. Now here we have to use the product rule, so it's a little more of a pain. There's also good practice for that. So let's take the derivative of the first function, which is x. Derivative of x is 1. Then times the other function, e to the negative x squared over 2, plus the first function, which is x, times the derivative of the second one. The derivative of exponential is the exponential, e to the negative x squared over 2. Then the derivative, using the chain rule, of what's in the exponent. And so that's first going to be -1/2. Okay, the negative, then over 2 part. The derivative of x squared is going to be 2x. All right, let's put all this together, make it look a bit better. And so we have e to the negative x squared over 2 plus 2's cancel out. And actually, this should now be a negative since we have the negative right there. Let's go ahead and make that negative. And it's going to be x squared, right? X here and x there, times e to the negative x squared over 2. Okay, so that's our derivative. Okay, now we know we have to find out where this is equal to 0. So actually, what's going to make that easier to do, let's go ahead and factor this. So what I'm going to do, I'm going to take a e to the negative x squared over 2 out of both. They both have that in common. And then what I have left here from this one is just 1, and here is x squared. Okay, and that's going to make it, this thing is going to be a lot easier to do this. Okay, and it's going to be a lot more like the first one we did. Although it's not a polynomial, it'll be more like that. Okay, so here's our derivative. Now, next, of course, find our critical values. So once again, set this equal to 0 and solve. And this is probably easier than it may look. And I'll explain why after I write it. Okay, what we can do then is that e to the negative x squared for 2 is always positive. You can check that on your own, but that's always positive, or exponentials are always positive. Okay, what that means, I can basically divide both sides by this and get rid of it for the process of finding my critical values. Okay. And since it's always positive, I don't have to worry about dividing by 0. And so what I'm left with is 1 minus x squared is equal to 0. Okay. And of course, just solve this. So negative x squared is equal to negative 1. Then divide both sides by negative 1, x squared is equal to 1. Then, but running out of space, let's finish it up right here. If you take the derivative, take the square root of both sides, x is equal to plus or minus 1, the square root of 1, which of course is 1. And these, once again, are my critical values, where the derivative is equal to 0. Okay. So those are places where the derivative can change sign. Since it's continuous, places where the derivative does change sign. Okay. Now, once again, let's do our sign chart again, same way we did. Okay, so here, negative 1, straight mark. And here we have positive 1. Okay, now, I'm going to make sure to include, now here, this time we don't make the same mistake, be a good habit of including this part, although we divide it through, unlike make sure don't make the same mistake like the first one, include this part here. But, as we'll talk about, it really has no effect in this particular case, but also is a good idea to include it. So our factors are e to the negative x squared over 2. Our other factor is 1 minus x squared. In this case, we just have the two factors. Of course, you always can have more in general. But then that's going to tell us the sign of our derivative. Okay. Now, as I said before, an exponential like this is always positive. Let's make this part easy. So this is just positive here, here, and here. It's positive everywhere. So it turns out, in this case, if we didn't include this factor, wouldn't change anything since it's always positive, but still it's a good practice to be in. Okay. So now once again, we'll do kind of a similar thing. Let's make this look more like a 1. Is let's actually think about some test values. So between negative 1 and 1, let's just go with 0. That's the easiest thing. But here, just negative 2, and here, positive 2. Doesn't have to, it can be any number in those intervals. Pick something easy to work with. Okay. Now here I have to think a little bit about this. Okay. So if we plug in a negative 2, plug in 2, or negative 2 or positive 2, either way, what happens? So plugging that in for x. Of course, if you square a negative, you get a positive. So that's going to be basically positive 4. 1 minus 4 is going to be negative. Okay, once again, all we care about the sign, that's just going to be a negative. Okay, now if I plug in 0 for x, 1 minus 0 is positive. Then finally over here, if I plug into 2, just as it was in this case, the negative 2, a positive 2 squared is going to be 4. That'll be 1 minus 4. That'll be a negative. Okay, and of course, we look down here, positive and negative is negative. Positive to positive is positive. Once again, a positive and a negative is negative. So that tells us what our function is doing here. So it's obviously decreasing here, increasing in the middle, and then decreasing here again. Okay, so where it's increasing is interval between negative 1 and 1. Now let's put the decreasing over here. So decreasing is from negative infinity to negative 1. And then again, from 1 to infinity. And then local maximums, local minimum values. So we have a local maximum. It's where it goes from increasing to decreasing. And it goes from increasing and decreasing here at 1. So at x equals 1. And then local minimum is where it goes from decreasing and increasing. That's at negative 1. So that's at x equals negative 1. Okay. Now, we kind of got a sneak peek of what our function looks like. But we know it looks something like this. So we know we have a local maximum at 1, local minimum at 2, and as we saw, so we've got a bit of a something like this. I believe it went through the origin. Like I said, to graph it, if you need to graph it, of course, just use a graphing calculator or Desmos. But here at negative 1, we have a local minimum, local maximum at 1. And once again, take a look at that again, make sure that's correct. And you'll see it is. Right. Okay, so like I said, these techniques were a lot more useful back in the day before calculators and computers when it was really hard to graph something. So that's the reason they were developed. They're still good for understanding what the derivative tells us and what the derivative is about, what information it gives us. So let's review. All right, so what we learned today are basically, well, actually, there's one more thing I want to show you real quickly. So let's stop at this last point right here. Let's do one more. I'm not going to go through the whole process, but I do want to show you one more thing before I forget. Down here at the bottom of the derivative test, it says if the sign does not change at C, then there's no local maximum or minimum at C. Let's take a look at one more where that's the case. All right, so let's just do a basic one. F of x is equal to x cubed. Okay, so you probably know what the x cubed graph looks like. Let's go back and graph that as well. So y equals x cubed. Okay. Now what happens is right here, as you can see, as we'll see, our derivative is going to be 0 right there. Okay. But it's not changing. It's not going from increasing to decreasing or vice versa. Let's talk about that. So if we approach this the same way, all right, first derivative. All right, so f prime of x is equal to 3x squared. Okay. Now, once again, if I find the critical values the same way, then we have 3x squared is equal to 0. Divide both sides by 3. X squared is equal to 0. And in this case, of course, what that means technically, you'd have plus or minus the square root of 0. The square root of 0 is 0. And 0 itself is not plus or minus, so you just have one value. Okay, 0. This is your critical value. Okay, I guess we do a really quick sign chart just to show it. So we'll have one critical value right here at 0. Okay, and actually we'll only have just 3x squared. That's here with the sign. I'm using my letters there. The sign of our derivative. Okay. Well, we plug in once again test value to be like -1 and 1. Pick whatever you want. Basically, since this is x squared, remember that's always positive. Anyway, I want to plug in, so it's always be positive. This is positive here and positive here. And so we just get the same sign. And so basically it says it's increasing here and increasing here. Okay. So essentially what that means is basically increasing everywhere, actually except right here at 0. So it's increasing negative to infinity, negative infinity to 0, and then also 0 to infinity, but not actually at 0. Okay, because it's equal to derivative is equal to 0 at 0. Okay, it's increasing. But here, if you notice, it's not changing sign. So f prime of x, it doesn't change in positive, negative, or negative to positive. So no local maximum or minimum. Okay. So in this case, it doesn't have a local maximum or a local minimum. And you can see that it's always increasing except for that point right there where it's actually to 0. And as we'll learn, the future will talk about something called concavity, and that's actually called what's called an inflection point, where basically this part of the graph here opens downward, this part opens upward, and where that changes is called an inflection point, and that's what this is. But basically, you can have places like this also where your derivative is equal to 0, but there's no change in the sign of your derivative. So in this case, it's not a local maximum or a local minimum at that point. So what we've learned so far is so basically that if your derivative is positive, the function is increasing, or the derivative is negative, it's decreasing. And of course, where it's 0 is either a flat line or basically that's where it changes. You have a local maximum or a local minimum. And you can also have those at critical values. In the first derivative test, it helps us to find not only where the function is increasing or decreasing, but also helps us to find, identify local maximum and minimum values. Thank you. Have a good day.